In today's episode of What Even Is That, I will be discussing viscosity. It is a very important property of a fluid. You feel the effects of viscosity every time you stir, pour, or swim. So let's get right into it. So by definition, viscosity is a fluid's resistance to flow. But in simpler terms, it's how much the fluid pushes back when you try to move it. Think of it like internal friction between layers of fluid. In this slide, we will be observing how certain fluids compare to one another. Air is nearly frictionless, meaning it has a very low viscosity. When we walk through air, we don't really feel any of its resistance to our movement. That's one way of thinking about it. Water, on the other hand, is about 50 times more viscous than air. SAE 30 motor oil is around 300 times more viscous than that. And then glycerin is another 5 times larger, and blackstrap molasses is another 5 times larger than that. So that would mean that it's 7,000 times the viscosity of water. As you can imagine, this fluid's flow would be highly resistant to deformation and would be very hard to move. Alright, so at this point we should conceptually be grasping viscosity. It's a fluid's property measuring a fluid's resistance to deformation, which is representing the effects of friction in a fluid. So let's get into some math now. Newton described how fluids resist deformation. For Newtonian fluids, shear stress is proportional to the velocity gradient of the flow, as we could see in the equation below. The first term to the left is shear stress, denoted by tau. The label is force over area, and in the metric system is newtons over meters squared. Notice the notations we use for shear stress. In this case, the y-axis would be normal to the surface, while the x-axis would be in the direction of the flow. Tau yx is the common case for when we have flow between two rectangular surfaces. However, if we had flow in between two cylinders and we were also using the cylindrical coordinate system, the radial direction would be normal to the surface, while the z direction would then align with the flow. In this case, we would have tau rz instead. Our next term is dynamic viscosity, which is denoted by the Greek letter mu. Its units are newton seconds over meters squared, which is also equivalent to kilograms over meters second. Dynamic viscosity follows the same definition of viscosity that we've been talking about. Please note that viscosity could also be represented by kinematic viscosity, which is denoted by the Greek letter nu. The equation for this is simply dynamic viscosity divided by density, as we can see in the bottom right corner of the slide. The final term is du over dy, which represents the velocity gradient of the velocity profile. In many problems in fluid mechanics, we will be able to assume a linear velocity profile, which makes the velocity gradient just become the change in velocity over the change in depth. We will see this in this example coming up. Using shear stress, we are able to find the resulting force of the fluid on the surface. In many problems, this will be referred to as the viscous drag force. Looking at the equation, we can see the total force exerted on the surface by the fluid is equal to the sum of differential forces. Think about it like forces being applied at super small points throughout the surface, and the total force is just the sum of all of them. The total resultant fluid force is found by integrating the shear stress over the wetted surface area, as seen in the surface area integral. By wetted surface area, I mean the surface area that is in contact with the relevant fluid. Let's look at an example of flow between two plates. We are given a flow which has a dynamic viscosity of 0.29 kilograms over meters second, a depth of 2 centimeters, and both plates containing a length and width of 2 meters. We are given that the top plate is moving at a velocity of 3 meters per second and the bottom plate is stationary. Using the previous equations, we could find the shear stress. We first notice that our only boundary conditions are the no-slip conditions at the surfaces. This allows us to assume a linear velocity profile. Using the no-slip conditions, the top of the flow must be moving at the same velocity as the top surface, which is 3 meters per second, while the bottom of the flow would have to be moving at the same velocity as the bottom surface, which would just be 0 meters per second since it's stationary. This makes the change in velocity through the velocity profile to be 3 minus 0, which is just 3 meters per second, while our depth is clearly 2 centimeters, which is the same thing as 0.2 meters from the given information of the problem. By plugging in dynamic viscosity, we are able to find shear stress denoted by tau yx, which is equal to 4.35 newtons over meters squared. Now, we must determine the resultant force on each of the surfaces. As previously discussed, we must integrate the shear stress over the wetted surface area. Since each surface shares the same wetted dimensions, they also share the same magnitude of force. The math in this case was very simple. The integral becomes tau times the wetted area, which resulted in a force of 17.4 newtons. However, the directions are different due to the normal directions of the surfaces. Since the normal direction of the top plate surface is negative while the shear stress is positive, the force must be negative. For the bottom plate, both directions are positive, which leads to the force also being positive. When tackling any problems in engineering, we should always ask if this conceptually makes sense. By looking at the picture to the right, we could conceptually understand what is going on with the direction of the forces. The top plate wants to move to the right. However, viscosity is trying to hold it back, analogous to friction. This creates a force to the left, which makes sense. The bottom plate is attempting to remain stationary, while the fluid's viscosity is attempting to pull it with the flow, causing a force to the right, which also makes sense. To recap, viscosity is a fluid property which measures resistance to deformation. It affects everything with flow, from lava flowing down a volcano to blood flowing through our veins. It is an important and fundamental concept in the world of fluid mechanics. So next time you stir syrup or feel resistance underwater, that's viscosity doing its thing. I'm Nicholas, and this is Mind to Matter, where we learn by building, breaking, and asking, what even is that? Like, subscribe, and stay curious.